Okay, so in this video we'll discuss something fun. Okay, and in this particular case, we'll try to see what is involved in sending a probe to outer space. And this is something that I hope people who do physics will learn, will appreciate, and they will learn to understand, how the concepts that they are learning in class can be applied to some real world problems. Okay? So, so the most vexing of uh, the possible applications of physics, right, and some of the most interesting of these is the uh, travel to outer space. And when I mean outer space, I'm talking about traveling to outer planets. So the outer planets are these are Jupiter, Saturn, okay, Uranus, Neptune. So Pluto is also a heavenly object. It used to be a planet before, but it doesn't have that status anymore. Okay, so it's really interesting to be able to travel to these planets, right? And we want to know why somebody would do that. Okay, the one thing is that we want to search for precursors of life. Search for precursors of life. Okay, things like water, okay, things like sulfur, okay, etc. Okay, search for presence of a magnetic field on these planets and the causes of this magnetic field. Okay, and the causes of this magnetic field. Okay, whether we have oxygen available, okay, and things like that. Okay, uh, so mankind would eventually like to, uh, you know, make other planets habitable, make other heavenly bodies habitable, to escape population pressures, for various reasons that we may not be able to think of right now. The second thing is we want to understand planetary geology. Okay, so what comprises the inner structure of these planets? What metals do they have? What minerals do they have? What is the structure of these planets underneath the surface? And that will kind of explain to us, what the phenomena were that caused the planets to take their current shape and form. Okay, so that's the second thing. The third thing is we will understand how the solar system was formed. How the solar system was formed. So a lot of these, okay, um, we can do by searching inner planets, that is Mercury, Venus, and Mars. But we know that Mercury is too close to the sun; it's unable to support a lot of life because of the high temperatures there, and Venus is extremely hot. Okay, because of it having a carbon dioxide atmosphere, which has caused a greenhouse gas type effect. Okay, and that leaves Mars, and Mars is barely habitable, if at all. Okay, uh, but people would be interested in knowing, what lies beyond. Okay, what lies beyond. So, so that's one of the reasons why we would like to explore these outer planets, right? So the problem here is one of escaping the Earth's gravity. Okay, so typically a big spacecraft like that has lots of instruments. Okay, and the mass of the spacecraft is typically like about 6 to 8 tons. Okay, 6 to 8 tons. It's pretty heavy spacecraft. So we can do this. We can put it on a rocket. okay, and we can launch it directly into space, right? So that's one way. So to do that, you will need to calculate the escape velocity, and so to do that, so you find the potential energy of the spacecraft on the ground is or the total energy of the spacecraft on the ground is, this is the kinetic energy, m being the mass and v being the velocity, and this being the gravitational potential energy. R is the radius of the earth and capital M is the mass of the earth. And so when the spacecraft escapes into outer space, let's say it has zero velocity, barely any velocity at all, and it has no potential energy, so the total energy is zero, and if energy is conserved, then that's what we have. So we have V equals square root of 2 gm over r. This happens to be about 11.2 kilometers per second. Okay? So it is a very high velocity. So if you look at the force required, okay, the force required to propel this spacecraft along with the rocket, right? So this is the mass of the spacecraft. Okay, it's capital M, uh, and then so F minus mg gives you capital M times A, right? Where A is the acceleration of the launch vehicle. So the force here equals capital M times G plus A. Okay, so if you look at like something like a PSLV, okay, PSLV, it's about 300,000 kilograms. Okay, that the mass of the PSLV, okay, is about 300,000 kilograms, and the acceleration at launch is typically is 40 meter per second square. This can vary depending upon the launcher, depending upon the the payload and whatnot, right? So now, so therefore, if you see here, effectively, the since g is approximately 10 meter per second square, so we find that a plus g is 50 meters per second square. So therefore, the effective mass, okay, of the spacecraft is about 1.5 million kilograms. Okay, so you need an enormous amount of thrust to put this kind of spacecraft uh, into uh, into outer space. Okay, so it's extremely difficult. So they have multiple stages. So the first stage burns, it detaches. The second stage burns, detaches, and so on and so forth. So there are several tricks to carry out. But even so, if you have a really big spacecraft, it's really difficult, okay, to launch it from a small launcher, okay, like a PSLV, which is really good. Okay, so what essentially happens in such a case is that they use this concept of a Hohman transfer. Okay, so you don't directly launch a spacecraft into space. So what you do here is that in the Hohman transfer, so what you do here is that you first you raise the orbit. Okay, you first put the orbit and put the spacecraft into an initial orbit. Okay, and let us say this is the initial orbit of the spacecraft, right? So when it comes close to the earth, well, let this is circular anyway, so you pick a point here and then you fire thrusters, okay, in this direction, so that the spacecraft actually moves out here, okay, into a higher orbit, okay, into a higher orbit. And so when the spacecraft comes back, so you give it another kick, so it moves yet into another higher orbit. So when the spacecraft comes out here, then you give it another kick so that this moves into yet another higher orbit. So let's say at some point you think that the spacecraft is far enough, then you fire thrusters one last time to inject it into outer space. Okay, so so this is a staged transfer to outer space. So for example, if you look at the Chandrayaan missions, right, or even the Mangalyaan missions, the way ISRO does it is through some a mechanism very similar to this. So the altitude is of the spacecraft is raised gradually, one step at a time, okay, using very carefully controlled maneuvers, so that this is extremely precise. Okay, so we know exactly, the location of the spacecraft. We know its velocity, and since this is done in stages, so we can do it one step at a time and not worry about throwing the spacecraft into outer space directly and hoping that everything works. Okay, so there is that. So now, we are faced with yet another conundrum. So if you look at, for example, it's a rough schematic of the solar system. This is not to scale, by the way. So we have the sun in between. Okay, so we have Venus. So I have there are several planets that are not in this particular picture. So for example, I didn't put in Mercury, I didn't put in Mars. So, but that's for a reason, right? So so what happens here is that if you look at uh, the outer planets, right? So the Jupiter is about 440 million kilometers, and that is already pretty far. Okay, so now what happens here is that if you want to get to Saturn, you'll have to get to Jupiter, okay, and travel the same distance that you travel to Jupiter one more time to get to Saturn. Okay, so Saturn is extremely far. Okay, so any missions to Jupiter and particularly to Saturn have to be very carefully planned out, so that you make sure that the spacecraft works properly. It has got all the instruments you need, and it's going to be able to survive in outer space for a long time, basically because there is intense solar radiation in outer space. Not only that, when the spacecraft reaches Jupiter or it reaches Saturn, it should be able to do its work and do its work for several years. So people want to run experiments and they want to repeat these experiments, so it takes a long time. So now what happens here is that so let's say you launch something. Let's say you have a really powerful rocket, right? And then you launch it towards Jupiter, and it goes really fast, right? So the spacecraft goes really fast. If it's going so fast, then it's just going to go past Jupiter. It's not going to get captured by Jupiter, and the same is true for Saturn. Okay, so you send a spacecraft really very fast. It's just going to go past Saturn, and you'll just have a flyby at a distance of several tens of thousands of kilometers or several hundreds of thousands of kilometers. You will not be able to make any measurements. You will not be able to do that. So the thing is, how do you get this thing to orbit Jupiter or to orbit Saturn? So what happens here is that when the spacecraft reaches close to Jupiter, then you start firing thrusters in the opposite direction and you decelerate the spacecraft, right? So when the spacecraft decelerates, okay, it gets partly captured, okay, gets partly captured by Jupiter, okay. And what you do here, instead of firing the thrusters to accelerate the spacecraft, you fire the thrusters to decelerate it. And so you take this orbit, okay, and lower the orbit to this one, then lower to here, and so on and so forth till you reach a stable orbit. Now, the thing with Jupiter and Saturn is that they have their own moons. So you can use the gravitational effects of those moons to slow down the spacecraft as well. Okay. Not only that, you also want to do flybys by Jupiter's moons. You want to do flyby by Saturn's moons, and so on and so forth. So that's a very interesting thing. But the point is that you need a tremendous amount of fuel to accelerate. Okay, and once you reach the planet, you need a tremendous amount of fuel to decelerate the spacecraft. Okay, so which means that you will not have much fuel left when you want to run your experiments. So what do you do? So the primary goal is to conserve fuel. Okay, primary goal is to conserve fuel. Okay, so that to operate the spacecraft, the probe, I'll call this a probe. Okay, and to run experiments. Okay, so here is something that is so as I was mentioning, we need to conserve fuel. So we need to conserve fuel to operate the probe or the spacecraft, right? Uh, During the orbit of the planet, and we need to run experiments, right? So in order for us to be able to launch a spacecraft uh, efficiently, in order for us to move the spacecraft through the solar system, and for efficient orbital capture, okay, so we need to use something that is called as a gravitational slingshot, right? So what the gravitational slingshot does is that it uses the gravitational attraction between the spacecraft and the planet to speed up the spacecraft. For example, so if you see the if you launch a spacecraft from Earth, right? So this spacecraft goes towards Venus, gets a slingshot from there, comes back to Earth, gets a second slingshot, goes back to Venus, gets a third slingshot, then goes to Jupiter, and if it's going to Jupiter as the final destination, then it gets captured by it, and if not, it gets another slingshot and goes to Saturn, right? So essentially, uh, when when orbital capture takes place, right? So here again we use a mechanism very similar to Hohman transfer. So so what we do here is that we fire the thrusters of the spacecraft in reverse, okay, so that the spacecraft is slowed down, right, when it reaches the planet, and then it gets, so for example, partially captured, right? So when it gets partially captured, then what we do here is we fire the thrusters in the opposite direction that we did before, okay? So that this spacecraft actually descends from a higher orbit to a lower orbit, okay? And then once the spacecraft had descended to a lower orbit, we'll fire the thrusters one more time so that it goes to the next lower orbit, and again we do that until we reach the desired orbit. Okay, so that's what happens. So now the thing is that uh, Jupiter and Saturn both have very complex systems of moons and rings, right? So these moons can also be used to slow down. Okay, the gravitational interaction between these moons and the spacecraft can also be used to slow down the spacecraft as it descends into the appropriate trajectory. So this can be done. Okay, but the say for so therefore, so one of the important things here is that if you as you know, if you essentially take the spacecraft and accelerate it too fast, okay, then you will not be able to get it captured, right? So you will reach the planet very quickly, but it won't get captured. So the gravitational slingshot is an efficient mechanism to that makes it possible for us to have the appropriate velocities. Okay, makes the operation of the spacecraft much more efficient. Okay, the only downside is that it takes a long time. Okay, it takes a long time. So in principle, you could reach Jupiter very fast. Okay, if you had a very powerful rocket, but you would shoot past that. But if you go using the slingshot route, okay, so using the slingshot route, it takes several years. So for example, to reach Jupiter might take about 5.5 years. To reach Saturn might take about 6.5 to around 7 years. Okay, so that's what happens. So let us consider the physics of the gravitational slingshot. So as I mentioned before, here the spacecraft that's travel with a mass m, okay, that is traveling with a speed of ui, and it goes past a planet, okay, which is traveling with an initial velocity of vi, and it has got a mass of capital M, and capital M is much greater than little m. Okay, so the spacecraft or the probe emerges on the other side with a final velocity equals roughly the two times the velocity of the planet plus the initial velocity of the spacecraft. Okay, so let's derive that using the equations of conservation that we have. So we can write the equation of conservation of energy, because there is no dissipation, as the kinetic energy to begin with, half mui square plus half capital M vi square equals half m uf square plus half m v vf square, right? And so if we consider this coordinate system where x is towards the right and the y coordinate goes straight up, so and assuming that all velocities in the positive x direction are positive, so we can write the equation of conservation of momentum, and this is mui minus mvi equals minus muf minus mvf. Okay, so we have that. So this was equation 1 and that was equation 2, and from equation 2 we get this uf plus ui equals capital M over little m vi minus vf, right? And from equation 1 we can get this expression uf plus ui uf minus ui equals capital M by little m, okay, vi plus vf and vi minus vf. Okay, so we have that. So this is 3 and that's 4, and so we divide 4 by 3, so you get uf minus ui equals vi plus vf. Okay, therefore uf equals ui plus vi plus vf. Now the planet is much more heavy compared to the spacecraft. So the planet might weigh hundreds of millions of tons, and the spacecraft might weigh a few tons, right? So therefore, so vi is approximately equal to vf, because the planet is not going to be affected by the presence of the spacecraft very much. So therefore, this uf is approximately ui plus 2 times vi, right? So you can actually show exactly, you can show that uf, okay, if you solve the equations by substituting the value of, finding the value of vf here, right, and sticking this in, right, so you can find uf equals ui, okay, ui 1 minus little m by capital M plus 2 vi divided by 1 plus little m divided by capital M. And since little m is much less than capital M, we have uf equals ui plus 2 vi. Okay, so essentially we are getting the same expression, but using a faster method. Okay, so there is that. So there we are. Okay, so we have found out the basic equation that tells us how the gravitational slingshot operates, right? We found out, you know, how to launch a spacecraft, very efficiently, by firing thrusters and raising the orbits, one step at a time, right? Uh, we also found out, that if you want to traverse this vastness of space very efficiently, we need to use a gravitational slingshot effect. Okay, so which speeds up the spacecraft, to the desired velocities, but it takes a long time. It takes several years. Okay, but that's why spacecraft need to be planned, and built well to be able to withstand the rigors of the radiation in space, to be able to operate for a long time without any human touch, be able to be automated, be able to communicate, have redundant systems, and so on and so forth. Okay, so there is that. This is a very interesting area. Okay. So we will have more videos on this in the near future. So in the meantime, let's enjoy what we have found for today.